Classical mechanics is the study of motion. We can illustrate the phenomenon of motion in classical dynamical systems with the double pendulum. A double pendulum is one pendulum hanging off a second pendulum, and it has 2 degrees of freedom, and at small energies it behaves in a nice regular manner. But at larger energies it behaves in a qualitatively different way. This qualitatively different motion, this irregular motion, is called chaotic motion. The distinguishing characteristic of chaotic motion is sensitive dependence on initial conditions. We can't demonstrate that too well with the physical double pendulum, but I'll try. So let's exhibit the motion for 2 very similar initial conditions. I'll start this one, and you have to remember the motion so that you can compare it to the next one. Well, it just sort of goes back and forth. So let's try another one and see if it does something that we identify as being different. So this is very similar to the first initial condition. There, so it didn't do that before. The little passover there. So that shows sensitive dependence on initial conditions. In simulation, where you have more precise control over the evolution and there's no friction, changing the end of this bar by 1 micron will result in qualitatively different motion in 20 seconds or less. And changing the position of this end bar by 1 angstrom, or roughly the width of an atom, will change the position qualitatively in 50 seconds. So very sensitive dependence on initial conditions is exhibited by this system. Now, we've seen one interesting, the defining characteristic of chaotic motion is the sensitive dependence on initial conditions, but such systems also exhibit transitions to chaos. So, for instance, at low energies, this system behaves regularly. At higher energies, you find chaotic motion without looking very hard for it. This is a transition to chaos. This particular system exhibits another transition to regular behavior at even higher energies, which we can illustrate. So at higher energies, you find a regular motion. It's regular because gravity doesn't matter. And then with dissipation, it damps down and goes into the chaotic state. But energy alone is not enough to tell you whether a system will behave chaotically or not. In a conservative dynamical system such as this one, whether you behave chaotically or not depends upon the detailed initial conditions. So let me illustrate 2 initial conditions with the same energy, one of which behaves chaotically and one of which behaves regularly. This initial condition behaves chaotically. And this other initial condition, which has the same energy, behaves regularly. It has the same energy because everything is raised to the same height, so the potential energies are the same, and it's motionless, so the kinetic energies are the same. But this one behaves regularly. So we've seen sensitive dependence on initial conditions, transitions to chaos, and the fact that whether you're chaotic or not depends upon detailed initial conditions. I'll finish with just illustrating once again the chaotic motion because it's fun to watch.